This lesson is part 2 of our bonding flowchart. In lesson 1, we talked about the polarity of bonds, and in this lesson, we're going to talk about the polarity of molecules. You're going to need the flowchart that you've already started and an electronegativity table. So grab those items and we can begin. So hopefully you remember from earlier in the year that to be a molecule, the substance needs to have covalent bonds in it. And if it's an ionic bond, we don't call it a molecule, we call it a salt. So over on the ionic side of our flowchart, let's write down that when the bonds are ionic in a substance, it's going to be called a salt. And an example could be NaCl. Notice how there's no little dash line between the Na and the Cl because the dash line means that they're sharing a pair of electrons. And in the ionic bond, they're not sharing a pair of electrons. The electrons have been stolen. All right, so to be a molecule, it has to have a covalent bond. So it either has to be nonpolar covalent or it can be polar covalent bonds. Those are all going to create molecules. We're going to start over with the nonpolar first. Remember, nonpolar bond meant that the bond did not have a positive side and a negative side. So we can look at the bond itself to look for a positive and negative side. We can also look at the whole molecule to see if the molecule as a whole has a positive and negative side. And if it does not, we can use the word nonpolar to describe both a bond and a molecule. So let's write down under the nonpolar part of our flowchart that when all the bonds are nonpolar in the molecule, then the molecule is also going to be nonpolar. Because if the bond doesn't have a positive and negative, partially positive, partially negative side to it, then the molecule itself cannot have a partially positive or partially negative side. And if we take a look at our example of two hydrogen bonded together, neither one of those is slightly positive or slightly negative. There's no charge on the bond, so there's no charge side to our molecule either. We could also write it as H2 to represent that molecule. Where it gets a little tricky is when the bonds are polar. So let's write down that when the bonds are polar, we need to pay careful attention to the arrangement of the molecule. Because just because the bond has a positive side and a negative side doesn't necessarily mean that when it's all arranged together in a molecule, that the molecule will end up with a positive end and a negative end. It all has to do with how symmetrical the molecule is and whether the charges are equal and opposite each other and end up canceling each other out. So let's split this part into two. We're going to have one side where we say when the bonds are polar and the molecule is symmetrical, which means no matter how you cut the molecule in half, it's mirror image on both sides. And it can't just be in one direction. You got to be able to cut it in half vertically, cut it in half horizontally. It should have to be symmetrical each time when you look at the two halves that you've split it by. And it will be a polar molecule if it has polar bonds and it's not symmetrical. Because if it's not symmetrical, the charges won't be equal and opposite each other and they won't cancel each other out. We're going to delve a little deeper into this, and let's start on the side where it says when the bonds are polar covalent, PC, and it's not symmetrical, it's going to be a polar molecule, because most people would expect if the bonds are polar, the molecule will be polar. So let's look at an example where that is the case. So when we were using the hydrogen chloride example before, we found the difference in electronegativity and found that it was 0.9. That's greater than 0.4 but less than 1.7, so it's going to be a polar covalent bond. So the electrons are going to shift towards the chlorine, making the chlorine partially negative, and you see that symbol by the chlorine, and the hydrogen becomes partially positive because the bond is polar. The bond has two sides, positive side, negative side. If we were to slice this molecule in half, we'll see that it's not symmetrical because we don't have mirror images on both sides because hydrogen and chlorine are two totally different elements, so it's not the same on both sides. And we can see that the hydrogen side is positive and the chlorine side is negative, so we end up with a molecule that has a positive side, negative side, which means it's a polar molecule. Remember, polar just means it has two sides. It can refer to two sides of a bond, positive side, negative side to the bond, polar covalent bonds. It can also refer to a whole molecule that has a positive end and a negative end, polar molecule. Let's look at a different example here. Here we have a molecule with carbon in the center and it's bonded to 4 chlorine atoms. Remember, each one of the dashed lines represents one shared pair of electrons, so each dashed line represents a different bond. But if we look at them carefully, we see they're all identical bonds. It's all between one carbon and one chlorine. So there's one type of bond in this molecule that's repeated 4 times around the molecule. I want you to determine what type of bond you're going to have between the carbon and chlorine, and you need to write down the math to support your answer. So take out your electronegativity table and determine what type of bond it forms between a carbon and a chlorine atom. All right, so hopefully you were able to find chlorine on the electronegativity table and you saw that its electronegativity is 3.0. Carbon is 2.5, so we're going to subtract those two numbers and the difference comes out to be 0.5, which is greater than 0.4 but less than 1.7, so it's going to be a polar covalent bond. That means the electrons are shared but not shared equally, and they're going to drift towards the atom that has the higher electronegativity, which is going to be the chlorine. So the chlorine is going to become partially negative, and all the chlorines are going to become partially negative as they all pull the electrons towards them, and that's going to leave the carbon as being partially positive. So the bond is polar, positive side and a negative side to each of the bonds, but because the molecule is symmetrical, we can see that the negative charges are directly opposite each other, and they're equal in charge because they're both chlorine, so they're going to have the same amount of negative charge, and since they're directly opposite each other, they're going to cancel each other out. So the two chlorines in this direction cancel, the other two chlorines directly opposite each other, they also cancel. So when we stand back and look at the whole molecule, we don't see a positive side and a negative side to the molecule. So that means it's a non-polar molecule, even though each of the individual bonds inside the molecule is polar and does have a positive and negative side. So if the molecule is symmetrical, even though it has polar covalent bonds, it can still end up being a non-polar molecule, which means that the molecule as a whole doesn't have a positive end and a negative end. Okay, so now it's your turn. You're going to take a look at the water molecule that you see on the screen. And first, I want you to figure out what type of bond occurs between the hydrogen and the oxygen atom inside the molecule. Then determine whether the water molecule would be considered symmetrical or not symmetrical. And then find out if the molecule as a whole would be called a polar molecule or a nonpolar molecule. So you're going to want your flow chart handy so you can start at the top and work your way all the way down to the bottom until you figure out what type of molecule it is. And you're also going to need your electronegativity table. So pause the video while you work, and when you're done, you can start the video back up again. Good luck. Okay, so let's check your answers. So to figure out what type of bond is inside the water molecule, we need to look up the electronegativity of the elements. And take a good look at that molecule. Yes, there are 2 hydrogen in the molecule, but for each one of those dashed lines that represent the covalent bond, there's only 1 hydrogen attached to each of those. So when we're determining the type of bond using electronegativity, we're only going to take hydrogen's electronegativity once. We don't multiply it by 2 because there's only 1 hydrogen in the bond. All right, so the electronegativity of hydrogen is 3.5 and hydrogen is 2.1. So we subtract those. Remember, you always want to subtract the smaller number from the larger number because we do want our differences to come out positive. And 1.4 is greater than 0.4, but less than 1.7, so that's going to be a polar covalent bond because the electrons are not going to be shared equally because oxygen has a large enough electronegativity that it's going to have an advantage over the hydrogen, which means the electrons are going to spend more time by the oxygen, which is going to make the oxygen slightly negative or partially negative, and the hydrogens then are going to become partially positive. Okay, now we need to figure out, is the molecule symmetrical? And many times students would look at this and say, well, if I were to divide the molecule like I just did with that red line, it looks like the 2 sides are symmetrical because they look the same on both sides. And they do. But for our purposes, when we're figuring out polarity of a molecule, the molecule has to be symmetrical in any plane that you cut it. And if I were to change that line and maybe put the line here, we can see that there's a hydrogen sticking out on the left-hand side of that line, but there's not a hydrogen sticking out on the right-hand side. So in this direction, it is not symmetrical. And since it's not symmetrical in every direction, it's not considered a symmetrical molecule. And we're going to say, no, this is not symmetrical. Now we need to determine, is it a polar molecule or a nonpolar molecule? And remember in our flow chart, we said that if it has polar covalent bonds, it will be a nonpolar molecule if it is symmetrical. But if it's not symmetrical, it's going to be a polar molecule. So this actually is a polar molecule, which means it has a positive side and a negative side. If I were to divide the molecule right there, like I did with that dotted line, you can see that to the upper right of the line, the oxygen is present and it's partially negative. And to the bottom left of the line are both the hydrogens, which are partially positive. So this makes the oxygen part of the molecule negative, the hydrogen part positive. We have two different sides to this molecule because it's not symmetrical, so it's going to be considered a polar molecule. All right, so you should have a flow chart that looks similar to the one that you see there on the screen. We're going to be using it quite a bit this week and next week and possibly even beyond, so keep it somewhere safe, but also somewhere where you can easily get your hands on it when you need to use it. All right, you guys did a great job today. Thank you for watching, and I'll see you soon. Bye-bye.